Hi students. In this lecture we will be learning about how we use science to better understand the environment. What is science? Well, science is a process for producing knowledge based on observations. We develop or test theories, proposed explanations of how a process works, using these observations. Science also refers to the cumulative body of knowledge produced by many scientists. Science is valuable because it helps us understand the world and meet the practical needs, such as finding new medicines, new energy sources, or new foods. In this section, we'll investigate how and why science follows standard methods. Science rests on the assumption that the world is knowable and that we can learn about it by careful observation and logical reasoning. The benefit of science, scientific thinking, is that it searches for testable evidence. As evidence improves, we can seek better answers to important questions. In this slide, we see some of the basic principles of science. Review this, and you can also see it in the textbook, Table 1.2. Ideally, scientists are skeptical. They're cautious about accepting a proposed explanation until there is substantial evidence to support it. Even then, every explanation is considered only provisionally true because there is always a possibility that some additional evidence may appear to disprove it. Scientists also aim to be methodical and unbiased. Because bias and methodical errors are hard to avoid, scientific tests that are subject to review by informed peers who can evaluate results and conclusions. The peer review process is an essential part of ensuring that scientists maintain good standards in study design, data collection, and interpretation of results. Scientists also demand reproducibility because they are cautious about accepting conclusions. Making an observation or obtaining a result just once doesn't count for much. You have to produce the same result consistently to be sure that your first outcome wasn't a fluke. Even more important, you must be able to describe the conditions of your study so that someone else can reproduce your findings. Repeating studies or tests is known as replication. Ideally, scientists deduce conclusions from general laws that they know to be true. This logical reasoning from general to specific is known as deductive reasoning. Often, however, we do not know general laws that guide natural systems. Then, we must rely on observations to find general rules. Reasoning from many observations to produce a general rule is inductive reasoning. Although deductive reasoning is more logically sound than inductive reasoning, it only works when our general laws are correct. We often rely on inductive reasoning to understand the world because we have few absolute laws. You may already be using the scientific method without being aware of it. Suppose you have a flashlight that doesn't work. The flashlight has several components: switch, bulb, batteries that could be faulty. If you change all the components at once, your flashlight might work, but a more methodical series of tests will tell you more about what was wrong with the system, knowledge that may be useful next time you have a faulty flashlight. So you decide to follow the standard scientific steps. You can see these in the text here in this slide. In systems more complex than a flashlight, it is almost always easier to prove a hypothesis wrong than to prove it unquestionably true. This is because we usually test our hypotheses with observations, but there is no way to make every possible observation. The philosopher Ludwig Wittgenstein illustrated this problem as follows. Suppose you saw hundreds of swans and all were white. These observations might lead you to hypothesize that all swans were white. You could test your hypothesis by viewing thousands of swans, and each observation might support your hypothesis, but you could never really be entirely sure that it was correct. On the other hand, If you saw just one black swan, you would know with certainty that your hypothesis was wrong. As you'll read in later chapters, the elusiveness of absolute proof is a persistent problem in environmental policy and law. You can never absolutely prove that the toxic waste dump up the street is making you sick. The elusiveness of proof often decides environmental liability lawsuits. Because bias and methodical errors are hard to avoid, scientific tests are subject to review by informed peers who can evaluate results and conclusion. This is step 6 in the scientific methods shown in this slide. The peer review process is an essential part of ensuring that scientists maintain good standards in study design, data collection, and interpretation of results. One strategy to improve confidence in the face of uncertainty is to focus on probability. Probability is a measure of how likely something is to occur. Usually, probability estimates are based on a set of previous observations or on standard statistical measures. Probability does not tell you what will happen, but it tells you what is likely to happen. Probability is often a more useful idea than proof. This is because absolute proof is hard to achieve, but we can frequently demonstrate a strong trend or relationship, one that is unlikely to be achieved by chance. For example, suppose you flipped a coin and got heads 20 times in a row. That could happen by chance, but it would be pretty unlikely. You might consider it very likely that there was a causal explanation, such as that the coin was weighted towards heads. Often, we consider a causal explanation reliable or significant if there is less than 5% probability that it happened by random chance. We also can use experimental design to reduce bias in our experiments. A natural experiment is when you observe natural events and interpret a causal relationship between the variables. It involves observation of events that have already happened. Many scientists depend on natural experiments. A geologist, for instance, might want to study mountain building, or an ecologist might want to learn about how species co-evolve. But neither scientist can spend millions of years watching the process happen. Similarly, a toxicologist cannot give people a disease just to see how lethal it is. Other scientists can use manipulative experiments, in which conditions are deliberately altered and all other variables are held constant. Most manipulative experiments are done in the laboratory where conditions can be carefully controlled. Suppose you were interested in studying whether lawn chemicals contributed to deformities in tadpoles. You might keep 2 groups of tadpoles in fish tanks and expose one to chemicals. In the lab, you could ensure that both tanks had identical temperatures, light, food, and oxygen. By comparing a treatment, that is the exposed group, and a control group, or the unexposed ones, you have also made this a controlled study. Often, there is a risk of experimenters' bias. Suppose the researcher sees a tadpole with a small nub that looks like it might become an extra leg. Whether she calls this nub a deformity might depend on whether she knows that the tadpole is in the treatment group or the control group. To avoid this bias, blind experiments are often used, in which the researcher doesn't know which group is treated until after the data have been analyzed. Good science is rarely carried out by a single individual working in isolation. Instead, a community of scientists collaborates in a cumulative, self-correcting process. You often hear about big breakthroughs and dramatic discoveries that change our understanding, but in reality, these changes are usually the culmination of the labor of many people, each working on different aspects of a common problem, each adding a small insight to solve the problem. Ideas and information are exchanged, debated, tested, and retested to arrive at scientific consensus, or general agreement among informed scholars. The idea of consensus is important. For those not deeply involved in the subject, the multitude of contradictory results can be bewildering. Are coral reefs declining, and does it matter? Is climate changing, and how much? Among those who have done many studies and read many reports, there tends to emerge a general agreement about the state of a problem. Scientific consensus now holds that many coral reefs are in danger as a result of pollution, physical damage, and warming seas. Consensus is that global climate conditions are changing, though models differ somewhat on how rapidly they will change in different regions. Sometimes, new ideas emerge that cause shifts in scientific consensus. These great changes in explanatory frameworks are termed paradigm shifts by Thomas Kuhn, who studied revolutions in scientific thought. According to Kuhn, paradigm shifts occur when a majority of scientists accept that the old explanations no longer describes new observations very well. When controversy surrounds science, claims about sound science and accusations of junk science often arrive. What do these terms mean, and how can you evaluate who is right? When you hear arguments about whose science is valid, you need to remember the basic principles of science. Are the disputed studies reproducible? Are conclusions drawn with caution and skepticism? Are samples large and random? Are conclusions supported by a majority of scholars who have studied the problem? Do any of these experts have an economic interest in the outcome? If you see claims of sound science and junk science, well, how can you evaluate them? How can you identify bogus analysis that's dressed up as a quasi-scientific jargon, but has no objectivity? This is such an important question that astronomer Carl Sagan has proposed a baloney detection kit to help you out. That's shown in table 1.3. In science, we frequently ask, how do I know that what I just read is true? Part of the way we evaluate arguments in science has to do with observable evidence, or data. Logical reasoning from evidence is also essential, and part of the answer lies in critical evaluation of evidence. An ability to think critically, clearly, and analytically about a problem may be the most valuable skill you can learn in any of your classes. As you know by now, many issues in environmental science are hotly disputed, with firm opinions and plenty of evidence on both sides. How do you evaluate contradictory evidence and viewpoints? Well, critical thinking is a term we use to describe logical, orderly, analytical assessment of ideas, evidence, and arguments. Developing this skill is essential for the course you're taking now, and critical thinking is also an extremely important skill for your life in general. Table 1.4, shown in this slide, shows you some of the important steps in critical thinking. There are many different aspects of critical thinking. Much of the process is about carefully examining what you are trying to accomplish and how you will know when you have the answer. Critical thinking also involves examining the source of information and how much that source influences the kind of information you receive. Analytical thinking helps you break a problem down into its constituent parts. Creative thinking asks, how might I approach this problem in new and inventive ways? Logical thinking evaluates whether the structure of your argument makes sense. Reflective thinking asks, what does it all mean? When reading this text, hearing the news, or watching television, try to distinguish between statements of fact and opinion. Ask yourself if the premise supports the conclusions drawn from them. Although most of us try to be fair and even-handed in presenting controversies, our personal biases and values, some of which we may not even recognize, affect how we see issues and present arguments. Watch for cases in which you need to think for yourself and use your critical and reflective thinking skills to uncover the truth.